that. So yes, I think I'm going to be sitting because that way people on the Zoom can see me if they want to. And also the cursor looks better. I hope you guys there in the Zoom can see the screen and the cursor. Is that okay, Sergey? Okay. Well, so I want to talk about what moves the heaven above, and oops, what I mean by that is this. So as you know, the first universal law of physics was gravity, and for a few thousand years we thought that the heavens move through this model of Aristotle, Ptolemy, and the Greeks, which basically they proposed that there was a mysterious ether that moves these heavenly spheres. So this is not so crazy. I mean, the model describes very well what you could observe at that time of the planets moving around us, and there is these fixed stars, but they didn't understood what makes those move, right? So for a long time, and a long time means like Descartes, even Newton believed in Descartes and believed that there was this ether that moved things. And as you know, after the work of some of guys I put here, well-known laws of Kepler, Copernicus, etc., we came into this idea that really what moves the planets and what moves Earth is gravity. And as you know, there is a long story after that, for a few hundred years, where we came into realizing that the universe, that these fixed stars were making a galaxy, and there was the island universe. And in the 20th century, then we start becoming aware of other galaxies. So my talk is going to be about cosmology, and the question is, can we understand cosmology using the laws of gravity? And this is the thing I want to address. So a very cool thing about gravity that in fact have become very popular recently, but has been there also for a few hundred years, is this idea of a black hole. You all know what a black hole is, but let me just remind you, one of the key features, classically, or in Newtonian mechanics, the way you will define it is an object whose mass is such that the scale of the object is such that the mass inside gives you a escape velocity of the speed of light. Okay, so Francisco told us about the launch of SpaceX. If the radius of Earth was a bit smaller, not even a SpaceX could launch out, right? Because we are trapped. And this is a very, very interesting concept, because basically it's telling us something fundamental that is related to just relativity, that events cannot go a speed faster than the speed of light. And this introduces a causal structure to the laws of physics. And this appears when you try to understand a star or many concepts that require speed of light. So in general relativity, one way to look at this is that the light cones, which I show here as a color, the past red, the future blue, the light cones are deformed so that when you get to the event horizon, which is the scale at which the escape velocity is the speed of light, then photons can come in, but they cannot come out, right? Because it's twisted, and then that's another way of saying that the speed of light is bigger than the speed of light. You are forced. So you allow things to go in, but not to go out. Now, you all know this, and this is a very interesting phenomenology about that. The way to understand this within general relativity is with metrics, and one of them, the most popular, is a Schwarzschild metric. It's not the only one you can understand a black hole, but the interesting thing is that when you look at a black hole from outside, for an observer that is outside, and you define a density, just because you are in empty space, you can define what mass the object has and what is the Schwarzschild radius. The density of the black hole, because it's the mass over the volume, scales with the radius square instead of the radius cube. And this also has important consequences that we will see. And one of them, which is interesting, is that we usually think of stellar mass black holes. And for stellar mass, the radius of the Schwarzschild radius is 2.9 kilometers. But if you think of a very large black hole, very massive or very large radius, then the density becomes very small. For example, for a black hole that is as large as our universe, that has 10 to the 22 solar masses, the density is much smaller than a few atoms per cubic meter. So this means that this idea that black holes are very violent and have these tidal forces and everything, well, yes, but if you are free falling and you are inside one of these things, the density is small and nothing happens. So you don't have to imagine yourself that a black hole is going to destroy you. The gravitational force is the same, but if you are in free fall, you don't feel that. And then the density is very small. And this is going to become important for my talk. So let me apply this concept of a black hole to the universe. So in the universe, what we do is we assume this cosmological principle by which is like a Copernican principle by which things should be more or less the same or larger scales over different positions in the universe around us. And this means in practice that we are going to assume that we have the same density in different parts of our universe. And this can describe also a star in principle, or an object that has uniform density, okay? Now, if you just assume that you have uniform density, you immediately get the Hubble-Lemaître law. So the consequence of having uniform density is that the distances scale with a scale factor, and this is the only way you can get this density situation. This is not, although this is a consequence of general relativity, you can also understand this in Newtonian physics. It's basically the homogeneity force you to have that the scales have to scale with a fixed factor, which we call the scale factor, as otherwise you cannot sustain the fact that everything is homogeneous as a function of time. This is the only way you can make things homogeneous. And the consequence of that is the Hubble-Lemaître law, which says that the distance between objects have a velocity that is proportional. The velocity is proportional to distance, and this proportionality is what we use the Hubble law, okay? So this is a bit more formally. You have a metric, which is the Freeman-Lemaître-Rosen-Walker metric. I put here the case of a flat topology. And then the Freeman equation is this one. It basically tells you that the rate of this expansion is proportional to the density. So the only way you can have a stable or a static situation is when the density is zero. Otherwise, you will have either contraction or expansion. Okay. Now, one thing that is interesting is to define what we call the Hubble horizon. What is the Hubble horizon? Is just the inverse of the Hubble rate. So the Hubble rate is inverse of time. So if you inverse the Hubble rate, that will give you a time times the speed of light. This will give you gives you a distance, okay, which is the Hubble distance. So here, instead of 1, you have to imagine a c, because I've been using units of c equals 1. So you can see that if you use the Hubble-Lemaître law and you put r equal 1 over h, then r dot equals c. So you have it. So the Hubble horizon is a distance in a system that has uniform density. It doesn't have to be the universe. It can be a star also. That distance is such that the speed is the speed of light the distance of from where you are. No, if you put yourself in the middle of this sphere, or if the space-time is infinite, then you can put yourself anywhere. It doesn't matter. So the difference, when it's infinite, you can do this around any point, and when it's finite, this is the solution when you put yourself in the center. So So why is the Hubble horizon interesting? So the Hubble horizon is very similar to an event horizon, but has some important differences. That's why I call it an apparent event horizon. What are the differences? Well, first of all, as I said, is 1 over h. Now, h is proportional to density, and energy conservation tells us that if you have an expanding fluid, then the density will dilute with the scale factor to the -3, because the physical distance scale with this scale factor, okay? So this means that the Hubble horizon is moving, it's not static. And in an expanding universe, it's always increasing. For example, if the density goes like 8 to the -3, the Hubble horizon goes like 8 to the 2/3. So as I said, this is also the same for a uniform cloud. It's the same situation. So the Hubble horizon increases, and one of the properties of this Hubble horizon, which is very similar to the event horizon, is that things can come in, but nothing can come out, okay? And this is just because of the speed of light, because of causality. So this means that the Hubble horizon defines a region here. This is the Hubble horizon for our universe right now. So the Hubble horizon for our universe is just 1 over the Hubble law. So it's basically something like, it's a very large distance. It's like 14 gigaparsecs. It's a very, very large, it's 4 gigaparsecs. It's 14 giga years, and there's a factor of 3 to convert from years to parsecs. So this is about 4 gigaparsecs. And what this means is that things can come in inside our universe, but nothing can come out, okay? And in particular, you can also work out perturbations, and perturbations freeze out. So basically, if you have a perturbation and the universe is expanding, any perturbation that is outside the horizon is frozen. It's like it has an infinite damping. And this is easy to see also by looking at the harmonic equation when you have an expanding surface. So this is important because, okay, the other difference with the black hole is that outside the event horizon, outside this Hubble horizon, which is not strictly an event horizon, you have matter. So in the standard universe, the idea, the cosmological model is infinite, space is infinite, and we have the same density everywhere. So it means we have infinite mass, infinite space, okay? That's the standard model. And so here you have the same density as here, and that's why this is not a black hole, because a black hole is empty outside and it has a finite mass inside, okay? But that's why we call it event horizon, because it has similar property. So this is a very important concept in cosmology, because what happens is that the physical distances scale with the scale factor. So what this means that as the universe expands, if you have a perturbation, the comoving size of that perturbation increases as the universe increases. So this is this red line. So here I put physical distance as a function of a scale factor. So in cosmology, a scale factor is time. So a perturbation will increase with the scale factor, but the Hubble horizon increases faster because it increases with the scale factor to the 2/3. And what this means is that if we're here now and we look at a perturbation, for example, we look at a cluster of galaxies of 1 megaparsec, and we ask where this cluster of galaxies comes from, we go back in time, there is a point where it crosses the horizon. So it means that the seeds for this structure that we see today were outside causal contact in the early universe. And this is unavoidable. And this is a real problem for cosmology. This is called the horizon problem. It's a killing problem. This basically means that this model is not cannot be attained. It's impossible, right? Because it cannot explain structure in the universe. Okay, so what is the solution for that? Most of you know the solution. I'm going to mention in a minute. But let me first rephrase this problem in a different way as problems to cosmology. Okay, here I put this, I had that, so you know the solution is inflation. So the idea is that you advocate that there is a time in the very early universe where the density becomes constant. It doesn't scale with the scale factor as energy conservation tells you. So somehow you break energy conservation, or you have to take into account some strange kind of matter for this to happen. And this is not so strange. You can do that with fields. If the field doesn't have kinetical energy and is in a ground state, you can have this situation. And then, because you have inflation, the Hubble horizon becomes flat because rho is constant. If rho is constant, h is constant. If h is constant, the Hubble horizon is constant. And if the Hubble horizon is constant, maybe this fluctuation exits the horizon, but was in contact with the horizon before, right? And this is the way you might want to solve this problem. I just want to stress here that if you calculate, you can also calculate in this situation, what is the true event horizon? What I mean by true event horizon. So the way to define a true horizon, event horizon is to throw a photon into the future and wait infinite time and see how far it can get. Usually in empty space, if you wait infinite time, the photon reaches infinite, right? So the event horizon is infinite. But, and this is the same in the Freeman-Lemaitre-Robertson-Walker metric. So the event horizon, if you throw a photon into the future, it gets to infinite. But if you are inside a black hole and you do the same, you get to the event horizon. And that's why you call that an event horizon, okay? So it's basically, the event horizon tells you that that's that concept that there is a point where you cannot escape from that region. Okay, so what are the problems with modern cosmology? So the first problem, which most people don't think is a problem, is the need of the Big Bang. So the first problem that we face in cosmology is the fact that the universe is expanding. Whereas gravity, one will think, the natural thing is that the universe should be contracting, right? If the engine for the universe was gravity, then the natural thing is that the universe will be contracting. But we observe that it's expanding. And the fact that the universe is expanding means that if you go back in time, you go to a singularity, right? Just because you end up, the density, as you go back in time, the density I said was a to the minus 3. So a's go to 0, then you get infinite density and 0 Hubble scale. The Hubble radius becomes 0 in the beginning, right? And this is the choice that cosmology have made. They say, well, to explain cosmic expansion, we need a Big Bang. We need that somehow there is a singularity, and this explains why we're expanding. And that I call the first problem, although most people don't think it's a problem, because basically this is telling us that we are outside the kingdom of gravity. You need something else to understand the expansion of the universe other than gravity, right? You need this Big Bang singularity. Now, the Big Bang singularity is what creates the horizon problem, right? Because this is the horizon problem again. So this is the same plot as before. This is physical distance. This is time. And the blue line is the Hubble horizon, okay? So it's 1 over h. I told you that Hubble horizon increases with time. And so if you look at the perturbation, it always in the past was outside the Hubble horizon. And that's the problem. And the solution to this problem, so you created a problem by assuming the Big Bang, and then you solve the problem by inventing inflation. Okay, what is inflation? Inflation is an early stage of the universe where the energy density becomes constant. And as I said, you can do this in several ways. One way is to, roughly, you can say that vacuum has energy. And so as the universe expands, because you create more vacuum, the density is constant, okay? Another way to look at this is to say that fields like classical or quantum fields have a ground state. And if you neglect kinetical energy and you are in a ground state of a field, this produces a density that is constant even in an expanding universe. So you have some potential ideas of how you can make this happen. But the problem with inflation is that it produces exponential expansion and this is why the Hubble rate becomes constant. The Hubble rate is A dot over A, so if H is constant, you have exponential inflation. And what you do is you dilute all the energy content of the universe, and you empty the universe to zero. So if you have inflation, the universe is empty, and we don't observe that. We observe, first of all, that is expanding, and second, that there is matter and energy. So inflation, you have to invoke a mechanism that you stop the inflation and you create matter and radiation. And this is called reheating, okay? So now here we go into this situation where we need to, in order to understand cosmic expansion, we need something that is different from gravity, that is something similar to the ether, because it's a field that we don't know. We call it the inflaton. We don't know the fundamentals of that field. And moreover, we need a mechanism to stop inflation and to create all matter in the early universe in such a way. Now, one of the problems of inflation is that for inflation to work, it has to happen at such a large energies that is outside the realm of experimentation. We cannot, this is energies of 10 to the 19, 10 to the 15 giga electron volts. And this is totally outside anything we can test in a lab. Okay, so yes, you can speculate about models of inflation, but we don't have a fundamental understanding. And therefore, inflation has a lot of parameters that relate to the few cosmological observations that we have today. For example, the nucleosynthesis abundance comes from the ratio of photons to protons. And this is a prediction of reheating. It's not a prediction, it's a fixed parameter from reheating. So you need to fix parameters to understand cosmology. The amplitude of fluctuations is another free parameter of cosmology, etc., of inflation. So, so this is one problem. The problem is solved by inflation. And also, do you remember the Big Bang? So a lot of people think that inflation is the Big Bang. So basically, that's the mechanism that explains that initial explosion. You have to somehow explain how inflation starts, and that will start the universe, because it will make an expansion, it will stop, it will have a reheating, but none of this is gravitational. All of this is physics that we don't know. A lot of inflation, there are different ways to make inflation. Sergei explained a few last week. You can do inflation modifying gravity, you can do inflation with inflatons. There are hundreds of models of inflation. Why there are hundreds of models? Because none of them can be tested. Well, that's why there are hundreds. Okay, fine. This is the standard model. We are fine with that. We work with this. Now, the problem is that this is not all. We have also measured that cosmic expansion is accelerating. And this is, again, totally against gravity. Gravity is always attractive. The expansion of the universe should be decelerating, should not be accelerating. And this problem, to first order, has nothing to do with inflation. This is something that happens later on, like close to now, okay? So in inflation, I told you, corresponds to constant density. It turns out that when we measure cosmic expansion, we find that the Hubble rate seems to be going to a constant. And we know that with high precision. Nowadays, it's between 2 and 3%. With Euclid, it will be better than 1%, okay? So it looks like the Hubble rate is going to a constant. Constant Hubble rate means constant density. So it seems that we are, again, dominated by constant density. You see it here. So you have, at the beginning of the universe, you have constant density. Then we have reheating, we have regular matter and radiation. And then now at the end, we seem to be dominated again by constant density. But look at the scales between this and that. Well, this is not even up to a scale. In energy density, this is like many, many orders of magnitude. The constant density in the early universe was 10 to the 15 giga electron volts. The constant density now is a few electron volts, is milli electrons, 10 to the minus 3 electron volts, right? So is a totally different regime. So now if this is produced by inflation, you need an inflation that stops, reheats, and then appears again later on at a totally different energy. And most people that do inflation don't believe that this has nothing to do with inflation, and so we call it dark energy. Okay, so again, this is not gravitation. So these problems with cosmology is telling us that basically, even though we understood gravity and we believe is the law explaining the universe, we need these extra ether things to understand the universe. Now, another way to look at this is the problem is a bit deeper than that. So this is the Hubble law. Now, if you put dark energy, the simplest form of dark energy is this cosmological constant. So you can think of the cosmological constant like a modification of gravity, or like this constant energy that is dark energy. But what we have measured with quite good precision so far, about 3%, is that this value is constant. So this means that in the future, the Hubble law will be a constant. And what this means geometrically is that we will have a constant Hubble, a constant event horizon, right? Again, it's not event horizon, it's a Hubble horizon, right? So you can see it here. So this is the Hubble horizon is becoming constant. Now this is much closer to what a black hole is. It's not yet a black hole, but it's closer, because remember, the black hole had a constant. It's a constant mass, and therefore it's a constant Schwarzschild radius, right? So this is something that is looking much more like a black hole. But it's not a black hole. Why? Because there is density here, there is density here, there is density here, and the density is the same everywhere at infinitum. This is the standard model of cosmology. It says that the density at a given cosmic time is the same everywhere, okay, everywhere. This creates this problem. If we now estimate what is the Freeman-Lemaitre-Robertson-Walker event horizon, remember I told you, if you throw a photon into the future, you can ask how far the photon reach. Now, if you have a constant here, the event horizon is no longer infinite. It becomes finite. So if you throw a photon into the future, anytime in cosmic history of the universe, the maximum will be this given by this R lambda, which is basically this cosmological constant or dark energy, constant dark energy, okay? So you can see it here. This is the value. So the event horizon is the red line. So now we have a Hubble horizon and we have an event horizon. Now, not even in inflation, if there is a constant here, if you throw a photon in inflation, even with exponential inflation, you will never pass this event horizon. The event horizon is there. So what you create, so all of this, the only thing that I assume is that this is constant. You then create this causal structure, which is very weird, where you have, this is any point in space-time, we are here. This is the causal region where things happen around us. This is frozen. So this is the universe outside the horizon. And then we have this event horizon. Anything outside here cannot even be reached by inflation. And then even outside the final event horizon, this is the future event horizon, which is the cosmological constant, the density is also constant. So the density is constant everywhere. How you create that? This is why I start this, because I had to explain this to the master's students, and I don't know how to explain that. How is the constant? I mean, with inflation, you can explain the first yellow part, but you cannot understand the rest, okay? Unless you modify inflation or you modify gravity, then you can do things, but with the standard model, you cannot do that. Okay, what is my alternative to this? Well, I think the interesting thing is to realize that everything I mentioned so far also applies to a finite cloud. So if you have a spherical symmetry and you have a finite mass, you have the same solution. You still have the Freeman-Lemaitre-Robertson-Walker metric. You have everything. You have the Hubble region, but now you have another region, which is the size of this finite structure. Okay, so this is a local cloud that has a finite mass, and it can collapse or expand, and the radius moves, and we know exactly how this radius moves. It's basically like the Hubble radius to the 2/3. And this is a solution to general relativity. There is no problem. In fact, The first solutions by Freeman and Lemaitre were like that. The first solutions for the cosmological model were finite. They thought it was a finite sphere. Then they realized that you don't need it to be finite. You can make R infinite, and this is what people took. But now let's go back and see what happens if the universe is finite, okay? If it has a finite mass. Well, what happens is this. If you have a finite mass, you immediately have a Schwarzschild radius. You have an event horizon just because you have a finite mass. And it's very easy to estimate what is the relation between this event horizon and the Hubble horizon, okay? And this is it. So basically, R is the size of this finite cloud, RH is the Hubble horizon, and RS is the finite mass, right? So basically, the fact that we see that the universe is larger than the Hubble horizon. Why we know that? We know that because if you go back here, for example, here, remember, we are here. This green line is what we can observe of the universe. So what this green line is if you take a photon back in time, and you say, where is this photon radially, physically, what distance is from us, you cover this green line. So first of all, the photon gets away from you, and so the distance to the photon gets larger and larger. But when you get to about redshift 1 or 2, something like this, then this bends. And the reason this bends is just because the universe becomes physically smaller and smaller as you go back in time. And so then the distance to this photon gets to a maximum and then gets closer to you again in physical distances, okay? So it's like if it is coming back, it's just because the universe is shrinking and the universe is coming to you. Everything will be on top of you, right? So this is what we can observe in the universe. And so you see, we can observe outside the Hubble horizon. And in fact, we have. In the cosmic microwave background here is 8×10⁻³ the Hubble horizon is 1 degree in the sky. And we see fluctuations in the CMB on scales of 300 degrees all around the sky. So it's only 1 degree is the Hubble horizon. So we know that our universe is bigger because we see it. We see these regions that are causally disconnected in the early universe. So we know that R is bigger than RH. So if there is a finite universe, that universe has to be bigger than the Hubble horizon. And this immediately tells you that R is smaller than the event horizon, so that we are inside the event horizon, okay? This is just a consequence of the fact that R is bigger than RH. So now, how this happened is, I'm going to talk about this in the second part of the talk. But just this is what the universe is telling us if you assume that the mass is constant, okay? Now, what happens is this. So if you are expanding inside the black hole, I told you before that you can never get out, right? Because it's an event horizon. And in the Freeman-Lemaitre-Robertson-Walker is the same. You have the event horizon in the future. You never escape this value. So what happens then is that the dynamics of the universe, when the universe is expanding, is bounded by the event horizon. And this means that the dynamics requires a boundary condition, okay? Usually when we solve Einstein field equations, we don't have boundary conditions. But in this case, if you are inside the black hole, you need a boundary condition. And this boundary condition turns out, when you work out what this is, I'm not going to show the calculation, but we have done this calculation in detail. It turns out that it's exactly the same as the cosmological constant. So it gives you a cosmological constant that is the thing that appears here in the Hubble law. So if you have a finite mass, that mass gives you an event horizon. That event horizon appears in the Hubble law as a cosmological constant. Okay, so what this is telling us is that observations are consistent with the idea that there is no dark energy, but just that the universe is finite, okay? And this part I'm not going to explain because it's a bit technical, but you have to believe me, or you can go to this paper and read it. It turns out that these two different models, the lambda cold dark matter model with dark energy and inflation, or a finite mass inside the Schwarzschild radius, have exactly, for a comoving observer, they have the same background. A comoving observer will observe the same thing here or there. And this is despite the fact that the comoving observer could be anywhere inside this blue region. So this is a local approximation. So basically it's a fixed mass, it's like a local perturbation. And if you are anywhere here, you see the same background as if you have an infinite 3-millimeter Orson-Walker universe, okay? And now, what are the consequences of that? If the background is the same, so we see the same 3-millimeter law and the same Hubble law and everything, what does it matter? It's just another interpretation for the dark energy, right? You just interpret dark energy as a constant mass, and that's it. Yes, but this has one important observational consequence, which is in inflation, the spectrum of fluctuations is assumed to be scale invariant. And this means that you can have fluctuations on all scales. Whereas in this universe, if you have a finite mass, there is a cutoff in the size of the fluctuations that you can have. This is basically because any fluctuation that is larger than this, you cannot see. You can only see fluctuations smaller than the cutoff. So this model, although it has the same background, somehow it might have different perturbation structures. And you can see it here. I mentioned this before, that this is the finite universe. This is the Hubble horizon. At the time of the CMB, most of the structure that we see in the CMB are structures larger than the horizon, okay? But these finite universe models will say that there is a cutoff that corresponds to about 60 degrees in the sky. So what is this number coming from? You take lambda, which is a measurement. We measure lambda from the Hubble law, and you convert lambda into a scale. And you say, what is that scale in the CMB? And this is 60 degrees, okay? So if this model is correct, you don't expect to see fluctuations on scales larger than 60 degrees. It has to be a cutoff. Whereas in inflation, there is no cutoff. Of course, now if I say that, people with these 100 models of inflation can come with a model that has a cutoff. And in fact, I have worked in these models before I came into that. Yes, you can put a cutoff in inflation as well. For example, a phase transition during inflation. There are ways you can do that. So this is not like a unique evidence that the universe is finite. But nevertheless, it's kind of interesting that when you look at the structure of fluctuation, so this is something we have worked out with Benjamin. Benjamin is here. He's not here. Okay, Benjamin Camacho is one of our students. So this is something that we have done recently, which is to measure what we call the scale of homogeneity. So the scale above which we don't see a structure in the CMB. Here you can see, this is a picture of a lambda cold dark matter prediction on large scales, smooth for large scales. And this is what we see in the universe. So you can see in the universe, we don't see structures on scales larger than these 60 degrees. It becomes very homogeneous. Whereas in a lambda cold dark matter, there is a structure on scales larger than 60 degrees. And this is the prediction of inflation is the green line, whereas what we measure is this blue line. And this is something that was known before. Sometimes this is called the quadrupole problem or things like that in the CMB. So there are hundreds of papers about that. And the significance of this result depends exactly how you do the analysis. But is something that everybody recognizes is significant, but we don't agree what is the significance of this. So this could also be explained as a fluke, as a fluctuation. Now, but we have seen more with Pablo Fosalva, who is also here. Okay, let me just say that this was interpreted, this is a letter to Nature in 2003 that interpret something like these results as the topology of the universe being a dodecahedral. So basically, it was assuming, if you assume that the universe has this topology, meaning that if you walk by here, that these are repetitions of the same thing, like a football ball, but only one of them is real and the other things are repetitions. If you assume that, then you can explain this data, but you also predict that there are circles in the sky that haven't been measured. So this explanation has been ruled out. I just mentioned one of the many explanations that have come into that. And another thing we did with Pablo Fosalva here is to feed the cosmological parameters to the CMB as a function of position in the sky. So if you look at different positions, you can measure the baryon acoustic oscillations and then measure cosmological parameters. And you can see that the cosmological parameters vary in the sky. They are not the same. They vary a lot. And you can interpret these variations as perturbations, as metric perturbations, okay? And this is one way to interpret that. And this is related to the famous tensions in cosmological parameters. For example, we have heard several talks when Luis and other people have been telling us that cosmological parameters here and in the CMB are different. And this could be these metric perturbations that we observe here. In fact, the amount, the scale of these perturbations and the amplitude agrees with what we measure in the CMB already. So this is, again, something that comes naturally as a prediction of this finite mass because of the cutoff of perturbations. So that's the conclusion. So my conclusion here is very simple, is if you assume that the universe is not infinite, but is finite, then this gives you a Schwarzschild radius. This Schwarzschild radius agrees with the event horizon of our mass and gives an explanation to lambda. So basically, lambda is just the mass. Lambda is 1 over m squared, the mass of our finite universe. Now, if this explanation is correct, this opens a lot of questions. Okay, for example, what about inflation? What about the horizon problem? What about dark matter? What about dark energy? So you solve something and then you open a lot of them. But, and I have answers to all of that, but these answers are a bit more speculative. I think this part of the talk is more solid, so I will stop here if you have questions. And then I quickly, in 5 minutes, I finish the rest. If not, you have to read the papers. So any questions about that part? So not questions about how this happened, but about if this is or not a good explanation of the universe.
So you say that in the standard model, basically you're showing that rho, so the density has to be homogeneous out to infinity. But can you have a situation where you have basically almost infinite in the sense that it's very, very, very large. But then at some point it's finite, right?
Yes.
So it has, let's say, no boundary in that sense, but it's very, very large. You cannot basically get there to check the side. So how these would be different from
So the question is, I don't know if you guys in the Zoom have here, the question is, how is this different from a universe that is very large? And this is a good question. So if basically this will be saying that the mass is much larger than lambda, and therefore it does not contribute to lambda. Then you do need dark energy to explain that H is constant. So yes, maybe the universe is very large, not infinite. Then the mass associated with that very large universe will give you a very small lambda. So this raises an immediate question: why the mass of the universe is 10 to the 22 and not 10 to the 40 or 10 to the 10? And of course, I have an answer for that, but I probably will not have time to explain it. Okay, well, I go on.
Just a question. You said there are no perturbations beyond the scale of 6 degrees because you cannot see. But wouldn't it be more correct to say that they are not there because there is no matter beyond the scale that corresponds to the outer radius? So how can you have perturbations if you have empty density?
Yes, yes. So I try to, this is a bit illustrated here. So the question is, if I'm arguing that the scale of these perturbations is larger than the size of the universe, how can we measure that in the CMB? Okay. And a bit of the answer to this is this plot that I put here. So we are in the middle of this sphere. This is supposed to be a sphere. This is the last photons that we see in the universe. They come from the CMB, and this is just a map of what we see, right? Usually these maps are shown in temperature. This plot was made by Pablo, where instead of temperature, we saw the cosmological parameters. Now, if you go a bit farther outside, so this is the distance to the CMB. If you go farther to larger distance, you get to the beginning of the Big Bang, to the singularity, which is this red line here. That would be the Big Bang. So if fluctuations originate in the Big Bang, this is how far it will reach in the time the Big Bang has between when it happens and the CMB. So this is what we call the Hubble horizon. So it's the smallest scales. But there are perturbations that are larger than these scales, okay? Now, these perturbations that are larger somehow they have to be originated there. And this is how inflation inflates between here and here and creates perturbations that are larger than the perturbations that you will expect if light has not happened during inflation. So in the background, in the black hole universe, where you have a finite mass, what happens is that the radius here, right? One way to understand that is that the radius is this finite radius, but you can still have perturbations 2 pi r that are larger than that radius. Okay, so these are the maximum perturbations that you can have. So basically, the way you can think about this, to answer this properly, you need to think about the next part of the talk, because the question has to do of how you create such black hole, right? And then I'm going to argue that you create this black hole with a collapse. And what happens is that once you enter the horizon, there are no fluctuations that are larger than the radius of that universe. But you can still see this in the sky. You can still, so basically this is not the radius of the black hole. The radius of the black hole is here. Well, anyway, it's a good question, but it's hard to explain without explaining the next part of the talk. So let me go very quickly through that. So the idea is that, okay, how we create a black hole universe? Well, the natural thing to imagine is that you can create that from a collapse, okay? And how is this different from the Big Bang? Is because you can start with a very low density. You just need some small amplitude fluctuations that eventually, through gravity, will grow into larger fluctuations. And in fact, when it becomes a black hole, the amplitude of fluctuations is not very large. It's small. So in terms of the linear perturbations. So how you solve these problems in cosmology? Well, the idea is that you don't have a Big Bang, but you have a big bounce, okay? So that you collapse into the black hole, and then you keep collapsing inside the black hole until you get to a density where you cannot collapse any longer. Why? My argument, and it's speculative, is that if you have a cold collapse without radiation, without pressure, why is cold? Because you start from a very low density, right? So you only have matter, radiation. When you have a very low density, you don't trap radiation. And you have a cold collapse. And when you have a cold collapse, you get to a point when the density becomes the nuclear density. And then you cannot collapse any longer because of how do you call that? Now,
exclusion.
Yeah, the Pauli exclusion principle. Sorry, the word didn't go Pauli. Yeah, so this is the same reason why core collapse supernova happens. Like if you collapse matter to a density beyond nuclear density, then Pauli exclusion principle tells you that there is a degeneracy pressure, and you react to that and you create a supernova. So as I said, this is speculative. I have worked out some of the details of that, and I'm working more on that. It might not be plausible, but it's something we can explore. But if you assume that this happens, then you solve the horizon problem, because you have before the collapse, so the collapse will happen here, the horizon will decrease, and this region that looks like it's causally disconnected was causally connected during the collapse. Okay, so that's how you solve the horizon problem. And I already told you how you solve the acceleration problem. So basically, you can work out the details of this model using the spherical collapse and work out analytically everything. In this model, we even have the nonlinear collapse work out analytically, and this is something I have done. And the situation that you have is something like this. So this is density, and this is the radius. So if you have a cloud of a finite mass that is collapsing, then it will follow this dashed line, because the mass is fixed. As it collapses, the radius will become smaller, and the density will increase like the radius to the -3. Okay, so you have these dashed lines. Now, here is the density of a black hole. So what happens is that when a cloud of a fixed mass collapses, when you get to the density corresponding to the black hole density, then it collapses into a black hole. Okay, and in principle, there is nothing preventing the collapse to go on inside, but then you are trapped inside the black hole. So this will happen for anything that has a mass bigger than 7 solar masses, if there is no pressure or rotation. This is a general solution. Except that you have this nuclear saturation density. If the mass is less than 7 solar masses, then you will collapse into a neutron star. You will have a core collapse, there will be an explosion, and you have a residual that will be a neutron star that is smaller than 7 solar masses. Okay, that's the idea. Now, in this idea, what happens is that the collapse time depends on the mass. So if there are fluctuations on different scales, there will be fluctuations on different masses. The smaller masses will collapse faster. They collapse very fast. For example, a core collapse of 1 solar mass takes 10 to the -6 seconds to happen. Okay, so what this then gives you a hierarchical scenario. It's very similar to the numerical simulations that we do today. So the first thing is that the neutron stars or the small black holes will collapse first, and then those collapse into larger black holes, right? And you have something like this. You have small things collapsing into bigger things, okay? And then the larger structures will collapse last. So if you wait 10 gigayears, something of the mass of 10 to the 22 solar masses will collapse into the black hole like our universe. And maybe this will collapse into something even bigger, which is related to what you were asking. No? There could be other things there. So anyway, so this is the idea. As I said, it's a bit speculative, but here is the idea that you form a structure during the collapse. This structure, as the universe collapses, gets outside the horizon. Then there is this big bounce, and these perturbations that were there outside the horizon affects the bounce, because the density is slightly different on very large scales. And this means that these perturbations that you create during collapse are remembered during the expansion. That's why you don't need inflation. It comes back in this way. Okay, and yes, this is the anthropic argument. So in very briefly, if you have a very large mass, you have more time to make galaxies and stars. For example, 1 solar mass, you only have 10 to the -6 seconds to make a star. You cannot make a star in 10 to the -6 seconds. You need larger mass. That's why lambda is very large, because to make a galaxy like our galaxy, you need a lot of time. And but the probability of having something with a large mass is very small. So there is a tendency between these two things, and you can do a calculation and estimate what do you expect for lambda if you need a mass as big as our galaxy to make an observer. And you get a value that is close to what we measure. Okay, so I finish here, and I open for questions.
Okay. We'll have a few minutes for questions.
There must be given expect to see that.
Yes, so the question is, if this black hole universe accretes mass, can we see that? This is a good question. So it comes naturally from this conclusion, no? That I was saying that we have this hierarchical collapse, and therefore there might be other things accreting. And I'm not sure about the answer. So there is, one of the problems is this, that in the spherical collapse model, the idea is that you create a void between, so when you collapse, it's a simplified version, but when you collapse, you create, we model as empty space between that you create when you collapse, right? So the mass is conserved. So originally the mass here was occupying all this space, but when you collapse, you empty the space around you because you are eating that space. Now, in this simplified version of the model, then there is no matter here that will collapse. This is one thing. The other thing is, if it does collapse and there is a black hole, does this reach you when you are collapsing inside the black hole? And this is not clear to me. My intuition is that no, that if you throw a photon into a black hole, because you are also collapsing at the speed of light, you will never see that photon. But it's something that I haven't thought too much about. But this, I think, is a good question.
Yeah, there was another.
Yeah, thanks. Very fascinating. You mentioned the homogeneity or the lack of power on the quadrupole. But there's another feature in the CMB, you're surely aware that the L of 20 or so, there's a consistent lack of power. Is this related, or what do you think about this?
Yeah, I know about that. We have looked at that. I don't know if Pablo, you have another.
Yeah, they're higher, but it's a consistent. There's many different L's.
Yeah, I mean, it not only happens.
Yeah, but
No, there are many features like that. Some of them are aligned. So the problem is that if you have a physical feature, then in Fourier space they will be aligned. So there is also an alignment of the quadrupole with the octupole, and there was some speculation that some of these low multiples could be related to some very large anisotropies. But yes, I don't know exactly how to answer that.
Any other questions? Yeah.
I was wondering one assumption, I guess, that relying on is that the speed of light is always been the same. And I was wondering if the source itself is relying on this assuming much larger speed because the early universe.
Yes.
Is something people look into.
Yes, so the question is whether that we have assumed that the speed of light is constant, whether this will change if the speed. Yeah, I mean, there are many solutions to these problems. I mean, mine is just one. In these solutions, there are solutions where the speed of light changes, solutions with G change. There are many, and those solutions are more or less plausible depending what you assume, what extensions of the modified gravity. I mean, what I like about this is that I'm using just classical general relativity. I'm not using any deviations, but there is also, when you talk about these extrapolations to large scales, why extrapolating to the classical is better than extrapolating to the non-classical? And I agree. This is a good question.
So if there are no more questions, let's thank the speaker again. And we have the pizza in the back.